What does it really take to send humans into space? We tend to picture the rocket, the launch, and the astronauts on board. But behind every mission are the thousands of interconnected systems and the engineers solving problems most of us never even think about. In this special From the Archives edition of Problem Solved, we're going back to May 2022, when IISE's Keith Albertson and David Brandt received a behind-the-scenes look at NASA's Kennedy Space Center, at a pivotal moment in the future of space exploration. From growing food for astronauts and preparing cargo for orbit, to maintaining the massive machinery that carries rockets to the launch pad, they discovered industrial and systems engineering at work everywhere they looked. And at the time of their visit, NASA was preparing for a major new chapter, Artemis, the program designed to return humans to the moon and help pave the way for future missions to Mars. Here's To Boldly Go from the Problem Solved archives.
I'm Keith Albertson, managing editor of IISE Magazine.
And I'm David Brandt, IISE's digital strategist. On March 25th, Keith and I were able to take a behind-the-scenes tour of Kennedy Space Center in Central Florida. We were able to visit several sites around the Kennedy campus and chat with NASA systems engineers working on various tasks at the space agency. Many of the photo and video highlights of the tour are featured in the May issue of IISE Magazine and on our YouTube channel at youtube.com/IISE channel.
As it turned out, the timing of our visit was ideal. It was just a week earlier that NASA rolled its Space Launch System rocket out to the launch pad at 322 feet high. It's the most powerful rocket ever built. It was rolled out for its first round of testing that began just a week later. Thanks to our host, Tammy Long of Apache Logical JV, a NASA partner agency, we were given special access to the Space Station Processing Center. That's where they grow crops and prepare cargo for the International Space Station. We also walked through the cavernous vehicle assembly building, toured the crawler transporter that carries rockets to the pad, and we got a close-up view of the moon rocket itself on Launch Pad 39B. The Artemis 1 spacecraft is scheduled to launch later this year in a program designed to return astronauts to the moon over the next decade. That's the first step toward human voyages to Mars.
You're about to hear audio from interviews and videos we captured during the visit, including interviews with an industrial engineer from Georgia Tech, as well as a previous guest of this podcast. And if you ever have the opportunity to tour Kennedy Space Center or even have careers with NASA, you'll surely understand as quickly as we did the immense pride engineers have working in space exploration, but only just begin to understand the enormity of NASA's legacy in reaching new frontiers. Welcome to the Season 3 finale of Problem Solved.
We began our tour in the Space Station Processing Facility, which includes numerous laboratories, processing rooms, and a large cargo loading area. The first stop was at NASA's Crop Laboratory, where plant scientist Lachelle Spencer and microbiologist Mary Humrick showed us some of the food they plan to grow in orbit and discussed the challenges of space gardening.
So this is a space crop production facility. It consists of a number of different labs. Across the hall here we have Greenworks, where a lot of testing, hardware testing takes place. We get engineers in on site that construct and test any number of things. We can do lighting, plant testing over there. The lights are off right now, that's why it's kind of dark. In this lab, we have a number of walk-in chambers and reach-in chambers. They're environmental growth chambers. They have the ability to adjust the temperature, humidity, and CO2 conditions. A lot of times what we do is we mimic ISS conditions in order to cultivate these plants. These plants are grown like 3,000 ppm CO2, and we want to evaluate how well they do in those environments, and they don't necessarily always like it. So we use these chambers to simulate that environment. After we grow all these plants, are they safe to eat? That's where Mary comes in.
That's where we come in. So we have a team of microbiologists that support all the horticultural plants and crops that we grow. And our job is to understand the microbiology of the plant, good and bad. So as we know, we all have our own good microbiomes. On humans, plants have the same thing. So these are root-associated bacteria that help the plant. But we also screen everything we grow that is intended to be consumed by the astronauts for food safety. So just as your food that is provided by a company, they do the same thing. They screen it to make sure the consumer doesn't get sick. So we have a crop planned of tomatoes that is going to fly in, I think, July of this year. So we'll do all that analysis first, and then the JSC medical team will look at our data and say, yes, it's okay to eat. So we have grown I think it's 14 different types of leafy greens and peppers, and they've all been able to consume, astronauts consume those on their space. So that's basically what I do in support of the platform.
And all this is to create food stuff for deep space travel, right? So
right.
If the astronauts don't have to take everything, they can bring it along with them and make it happen on
Right. So the horticulture side of things is to test a lot of different crops, and from those you select based on how well they grow. So our aspect is, well, let's look at the system and the microbes, and is it also appropriate to fly in a small system like veggie or some other type of system, some of the things that are planned for the future as well. So, and we also are starting to work on the introduction of some good microbes, like a biofertilizer. So that's an area of investigation.
not just food in the tube anymore.
What's that?
Not just food in the tube.
Yeah, that's right. I mean, they really, I don't know if anybody has seen any of those images of the chili peppers that Michelle was instrumental in that. So they really, I think for the most part, really enjoy having fresh, good, safe produce. So
I can talk about in a nutshell how we got the Espanola chili pepper to the advanced plant habitat. It started right here in this lab, this chamber over here. We screened dozens and dozens of chili peppers to make sure that they were compatible with the environment to which we wanted to grow. Did they have good germination? Did they have the right size? Are they compatible with LED lighting? And we did them in these chambers. So about 3 years ago, we grew chili peppers to the extent, but right now we're testing strawberries. So maybe in 3 years we'll have strawberries, right? So not only did we screen multiple different cultivars, meaning varieties of chili peppers, we used these chambers to make sure that they were the right size. Then we moved over to GreenWorks and tested how well Espanola chili peppers grew in an APH analog system. We did that over there. And then from there, it went over to the APH Engineering Demonstration Unit, which is the EDU. And we did 2 tests in there to evaluate its compatibility with the hardware. So before it went to IISE, all that work started here with the people in this lab. That project was also successful because of the seed sanitization methods that were developed by Mary's team here. If they were not sanitized correctly, we could introduce pathogens like Fusarium into the system that we don't have the ability to clean out. If they're not sanitized correctly, they won't germinate, they won't be viable. So she's here because she's an integral part of our team, just like the things that you see here. So hopefully one day we'll have strawberries here. The next step for these strawberries will hopefully be Chipia. We're currently testing them in the aero gardens that will be used at Chipia, which is a 1-year analog, which will have a food production aspect. A small portion of it, the analog fruit will be growing these fruit, hopefully. We're still testing it. But right now, we do have a list of leafy greens, tomatoes, and peppers. And leafy greens, tomatoes, and peppers that will also be tested and grown in Chipia. Those crops started right here, right? So,
space taco?
Oh, yes, the space taco.
They'll be in there for 3 years.
Excuse me?
You said they'll be in there for 3 years.
So, the Chipia analog will run for 1 year, and I think it's 3-year tests. They'll do it 3 times. The food production aspect of Chipia, there's, I think it's 70, don't quote me on this, but it's only a portion of it. They're only going to be growing their crops for certain portions of the 1 year. scenarios. But that's the next step for these, hopefully. We worked with the USDA. They gave us a genetically modified plum. It was modified so that it flowered and fruited within a year. And so this work was done over in the SLSL lab. So we tested a number of their different modified lines to see how compatible it was with controlled environments and different CO2 levels. So we have tested trees. Yeah.
So one of the, I'm just looking at the chart.
Yeah.
One of the great environmental challenges is growing in an environment like this is water use.
Yes.
Because I see that noted on here. You can't just go turn the hose on them like you can the plants in your garden. So what are some of the engineering processes you go through to sort of decide what plants can survive that?
Well, for this test, we did things like stomatal conductance measurements to evaluate how much water the plant gave off. And what we found was that the genetically modified versions were unable to open and close their stomata well. So they actually utilized way more water than the unmodified versions. So while this is a great construct terrestrially, maybe it's not quite ready for extraterrestrial use because the water use was exponential.
Yeah.
So we just couldn't keep up with it, at the time.
And you have to
6 years
try to go through the experiments and go through the process and figure out which plants are going to be able to make it.
That's one of the things we do figure out in these chambers, which crops are more water hungry than others. So that's one thing we do to figure out. Let's see if I got some microgreens to show you guys.
Okay.
So another project that we have, we're evaluating microgreens. Microgreens are small little plants that grow within 7 to 14 days. They're jam-packed with nutrients. They'll be an easy crop to grow for potential crew members to consume. They're of interest because, one, they're easy to grow. They germinate quickly. They have way more nutrients in them per gram than maybe a standard size crop. And if you're short on time, you can sprinkle little microgreens on them. I have a picture of them, so you can't really see them in there. But we have screened over 70 different types of microgreens in this lab, from basic ones like mustard, collard greens, kale, to more exotic things like quinoa, cantaloupe, and even herbs like basil and parsley we've screened as microgreens. And this would be really great to grow it in 14 days, sprinkle it in your tacos, sprinkle it in your salad. It's not, our goal is not to make a giant salad. Our goal is to supplement the diet, to add benefit and psychological benefit to these meals and spice them up and add different textures and flavors.
Yeah, you want nutrient packed into a small space, basically. You want something that's easily transferable, but with a lot of nutritional value, because otherwise it's not going to have the same needs to fill the astronaut's needs.
And additionally, we found that the food that they will leave with, actually the nutrients degrade over time. In about 3 years, a lot of really valuable nutrients like vitamin C and vitamin B1 degrade over time. So we're trying to supplement that vitamins with that. One last thing. So these chambers are great when you have a huge experiment, right? But what if you want to test different light treatments? What if you want to test different CO2 treatments? And we don't have enough chambers, right? We have the ability to test 6 different light treatments, 6 different CO2 treatments, 6 different anything treatments with the use of these chambers called the Exciter chambers. They were custom designed and custom built by Lawrence Koss on our team, and they have the ability to have their own micro environmental system in each of these chambers. So a number of researchers have used them to introduce a number of different treatments to plants. And this kind of condenses our science so we can get a lot more science in a smaller footprint.
After a tour of the cargo bay, Randy Gordon, a Georgia Tech industrial engineering graduate and cargo integration manager for Gateway Deep Space Logistics, provides an overview of the processing center operations.
We saw today, Randy, how cargo is prepared in laboratories, then prepared in the cargo bay to be sent into space. It really is, as you are an industrial engineer from Georgia Tech, it really is a process that I think is familiar to industrial engineers in manufacturing and supply chain on how things progress along those lines and the logistics involved just with space, in this case being the final destination. Those really tie together, don't they?
They do. I thought, for most of my career, I thought of that assembly line process as a good analogy. For cargo and science experiments going to IISE, you have researchers and hardware developers around the country, really around the world, working on designs. Then they'll move into serious design reviews, prototype development, hardware development, and finally they get some flight hardware, and most of it's built around the country and other places. But as you approach launch, it gets shipped here for a phase that's launch processing, which can usually involves a final checkout, some final installations, time-critical activities like loading live biological samples into an experiment. It needs to be done really close to launch, so that'll be done at this phase. And that's what this team here at Kennedy Space Center does. It hosts these different teams as they come here for those final steps. We have labs, we have different kinds of processing space here that we help them set up. Some tasks that are a little more safety critical are done here because you don't want to do like load in the oxygen tank at a really high pressure and transport it across the country. So our teams will do that kind of work here. And it all leads up to the days and weeks before a launch on like a SpaceX resupply mission to ISS, for example, where those teams will do that final bit of work. They'll hand it off to a transportation team that will deliver it to SpaceX, our launch provider in this scenario, and then they'll take it to the next phase of loading it into their spacecraft. And then, the mission just continues as you count down to launch, you go to station. So it is this sequence of events. We have this little slice that's at an interesting time critical part as you lead up to launch, so that makes it pretty exciting. But yeah, it just leads to the next phase.
And you were talking before, too, on how the facilities themselves evolve as space travel has evolved. The early days of space travel were a whole different priority. You had the space shuttle era. Now we've gone into the ISS era with Gateway to follow. And you're repurposing a lot of the laboratory space based on different needs, and in particular with commercial interest coming in as well. That's a constant process, isn't it?
It is. It was really exciting here. It's challenging and exciting. As shuttle ended in about 2011, this building had been used for final assembly and checkout of the large modules that make up space stations. So your U.S. lab, different nodes, different European labs going to station, a Japanese lab. So big modules had come through this building. As the assembly of the station was completed and station ended, this building's purpose needed to evolve. And at that time, as the station was fully built out, the amount of science we could do ramped up. We had a bigger crew, we have a full space station, and so the goal at that point was to really maximize the throughput of science. And this building got really repurposed to handle all those science teams that need to do the final preps we're talking about for their payload just before we hand it off for launch. So we kind of scrubbed the whole building looking for every bit of space we could turn into a lab, and we did that. We developed a plant growth lab where plant research is done. That's kind of exciting for Kennedy because we do not only that final launch site prep for those, but we actually do the research and development of those payloads.
And we also learned how, as the International Space Station's life comes to an end by the end of the decade, the next step is going to be more commercial modules, more cooperation between commercial interests and NASA on how modules are used for different experiments, and then ultimately that's going to transition into Gateway. So that's another part of the evolution.
It is. I think it'll be an exciting time. The Into Space Station will be tough for me. I've worked on it for a big chunk of my career. The plan is for it to end in 2030. At that time, we hope to have Gateway fully operating in lunar orbit. So we'll be sending crew and science and cargo type things, hopefully from this facility, to support that. But we're also, NASA is stimulating development of commercial space stations to replace ISS in low Earth orbit. So hopefully we'll have those destinations too, and maybe this facility will be used to support research and experiment type work going to those stations also.
And as we roll toward the start of the Artemis program, we have the rocket on the pad out there for the first test of that vehicle. Gateway is starting to become more of a reality for everybody here. As that program comes online very soon, there must be sort of a sense of urgency as you move forward to really getting all of your processes in place.
Yeah, there definitely is. I think it'll be exciting as we get into some test launches of Artemis. That'll be very exciting. And then there's a lot of work going on now to develop the core modules that'll be Gateway, that orbiting kind of command center around the moon. The one we're working on is the Gateway Logistics Services, and that will supply cargo and science gear, astronaut crew supply type things to Gateway. And it's modeled off the commercial approaches we've taken since shuttle to resupply station.
The staff at the processing facility is beginning the transition to Gateway. That's an outpost that will remain in lunar orbit to supply Artemis astronauts traveling to and from the moon. Fleet Manager Sean Butts, a previous guest on Problem Solved, discusses how lessons learned from the International Space Station will apply to Gateway. Sean, we talked a little bit about the transition from the ISS to Gateway, and now it's with the Artemis program coming online soon, it's becoming real. What are the next steps as you've been preparing for so many years of this module to orbit the moon and be a supply module? What are the next steps as you ramp up toward these missions?
Well, as we started cutting metal on the pieces of Gateway, and things are really starting to happen with not only the domestic partners that are supplying parts of Gateway, but also our international partners who are ramping up to provide modules and all kinds of system support. We're really starting to get into the weeds of understanding more about what we're all going to be doing on Gateway. So within the logistics world that we support, we support the Gateway Logistics Services contract to procure commercial services to carry cargo and supplies to the Gateway, and also to take trash away. We're getting more and more in depth about really understanding with the team on Gateway what the Gateway, like think about what a day in the life of Gateway, or maybe a better term is like a week in the life, like an orbit around the moon for Gateway, the NRHO orbit is going to be about a week. So we're getting into more conversations about operations, and the operations teams are starting to share with us a lot of knowledge about, more detailed knowledge about the studies, the way the Gateway is going to be operated. And from our perspective, they're identifying a lot of problems that they don't have necessarily solutions to. So we offer a great deal of flexibility to the Gateway program as a reusable, well, not a reusable element, but a customizable element. Every logistics module that flies to the Gateway, it can be a one-off with a life of about a year, and we're intending to supply Gateway about one flight every maybe 15 years. So over that 15 years, what kind of things Gateway needs are going to evolve, and the flexibility we offer can be one way to help solve problems on Gateway. So the most recent conversations we're having are Gateway identifying long-term things that they don't have solutions to, say like running out of fuel. Like if we want to extend the life of the Gateway, but we need to be refueled, are there solutions that logistics can provide? How would we either supply more fuel or maybe augment the Gateway's ability to orient itself in space, change its attitude, how it points, how it maintains its orbit in NRHO? Are there logistical solutions we can bring through the logistics contract to solve those types of problems? So it's more than, for us, it's exciting to kind of think about longer term problems that aren't just how do we get more stuff to Gateway, but how can we use our contract and our commercial partners' innovations and solutions that they're coming up with and ideas that they're coming up with to really help the Gateway execute its mission in space, focus on the science and the research and astronomy and human presence in space, and leave some of those weird, challenging systems problems to us in the commercial industry to try and solve.
As Gateway ramps up, and as you said, you encounter more problems, there are going to be more problems that you can't even anticipate, I imagine. How do you sort of plan for future troubleshooting? Because even dealing with something in low Earth orbit and something in lunar orbit, it's just amplified the number of challenges you face. So how do you approach those to make sure you're preparing for what you might encounter?
For NASA, I think we've been internalized pretty well in our culture that the best way to prepare is to look at what happened in the past and to not forget the lessons of the past. So NASA has a very thorough and well-intentioned lessons learned program to capture programmatic lessons learned from any and all NASA programs. So the IISS has been an amazing proving ground to kind of show the types of problems you encounter in low Earth orbit, as far as having humans operating and trying to live in space and operating a very complicated system outpost in space. Gateway is going to encounter all of those same problems, but the luck is we've at least had a chance to identify them before and try different solutions to address them. I mean, granted, they may be low Earth orbit type problems. Inevitably, there's going to be some other problems we can't solve yet that we haven't run into when we're trying to deal with an outpost around the moon that's not manned 24/7. So that's new. That's not ISS-like, right? So trying to figure out how do systems stay operational? How can we make them more reliable? Because they're not going to be able to be maintained. You know, if a fan goes out in the Gateway and there's no crew on board, you're stuck with a dead fan until you get there the next time. And if that stuff starts adding up, then you're going to be blowing all your research time fixing and maintaining your space station. So reliability for Gateway is paramount. And I think that's a core lesson learned from ISS is they're really worried about maintainability. Because they know we have so much data from the ISS about what it takes to operate that station. And that's a real concern with NASA is devoting too much crew time to managing and maintaining your plant. Right? You don't want to have to maintain your plant 24/7 if your plant can't produce whatever its output is. And in our case, the output is hopefully science and inspiration.
And we talked before, your team was already in the process of growing, and it's been, I think, a little bit more than a year since then. How has your engineering team grown since then, and how are you beginning to specialize in some of these problems with what Gateway is trying to accomplish? You know,
we actually haven't grown as far as like head count per se, but I think the team growth as a cohesive unit has really been what's been changing. And, you know, it's been challenging since we last talked. We've talked in the midst of the pandemic. We're just starting to wind down. You know, here we are on the Space Center. This is only my second day back at the Space Center in the last year. So there's been a lot of change. But as far as the team, it's seeing everybody kind of come back together and get back into the rhythm of being comfortable being around and trying to figure out how to work as a team together in the same space, whereas before we were all doing it from home. So just seeing the team kind of get comfortable in their roles and to start to take ownership of some of the responsibilities they have. We are quite a small team, and we're putting a lot on each individual engineer we have within us, within Deep Space Logistics, to really own their role and their responsibility for working with our commercial providers. And we're still not fully funded yet, unfortunately, in logistics, so we're still in kind of a quiescent mode, waiting for that fully funded contract to kick into high gear. So mostly it's priming the pump so that when our provider is on board, the team in Deep Space Logistics, the commercial team, or the civil servant team and our support contractors have everything lined up. Process-wise, I think you've talked about processes in some of our discussions here today about making sure we have all of our internal processes in place to make sure that we're a finally running machine when we actually hit the ground running and have a contractor to start working in space mission development and flying Gateway.
The Crawler Transporter, known affectionately as the Beast, is a 6.6 million pound hauler built in the early 1960s to carry rockets to the launch pad. It performed that task in mid-March by taking the SLS Artemis 1 rocket to the launch area for its first test. Here we are given a tour of the vehicle by Stan Schultz of Jacobs, the Crawler's maintenance and operations contractor.
I think just from the standpoint of what systems engineers would be interested in what you guys do, because a lot of folks in a factory, for instance, are involved in maintenance and just sort of maintaining equipment. And the scale of this, though, is certainly so much bigger. But I think it's something that they can relate to in terms of keeping your machinery operating.
Well, a lot of those things, I may run something too. And a lot of places are like this, though, also. They can't actually run to failure because it costs too much for downtime. So, you know, for us, like I was saying earlier, you know, we can't afford any downtime. We can't stop. So when we're actually maintaining these things, one of the things you do before you check something out, before you take it out, you want to make sure it's working properly. So we do, and it's just like your vehicle. If you let it set for 2 months, go see what happens to it, right? It's the same thing with this. So we, every 2 weeks minimum, we operate this thing, we move it. As we're running out, before launch, we check all of our systems. We call them X-5 days before we start doing a bunch of maintenance in preparation for the roll, getting our supplies, just checking all those parts. And then we do the final day, we actually maneuver, make sure all our steering and everything, all the systems are activated and responding correctly. So I think that checkout also ahead of time is imperative, to verify all the subsystems are, running perfectly.
Yeah, well, that's like modeling in an industrial situation. You want to check everything out ahead of time and troubleshoot before the fact.
Right. And let's be fair, we've done this for a while. So we know some components and things that are higher maintenance and things that actually need to be routinely, inspected. Well, you might be able to get away with a 6 month, maintenance PM on something. Other things, other items require a monthly, check.
Right.
So those are some of the things. And as you run a system, the more intimate knowledge you have of it, the items that need a little more care versus the other. But with respect to that, tolerances, having data, that's the thing.
Mm-hmm. What kind of modern data gathering do you have? Do you have sensors and a lot of more sophisticated equipment maybe than they had originally when the Saturn rockets were rolling?
Right. So, good point. A lot of things that we do now, a lot of our strain that we're looking at, our loads analysis, we actually have sensors knowing what the guide tubes themselves are seeing, especially when you start going up the slope of the vehicle. So we know we keep a check on all those things and make sure that we're not loading up one side versus the other. Our leveling capability, knowing exactly where we're at relative to the other side is important as well. So we actually have vibration analysis that we're looking for wear, excessive wear. And so that's something they didn't have back in the day.
Yeah, absolutely. Yeah.
Right.
In the processing center's high bay cargo area, we were able to climb aboard a full-scale prototype of a Sierra Space inflatable habitat. It's one of many commercial projects that may support NASA's Artemis missions. While we were inside the hab, John Koroshetz, Vice President of Advanced Programs for Sierra, discussed how industrial engineering principles are fundamental to space engineering.
So it's actually a tie-in, as Randy's talked about, we see a huge commercial market. And in fact, NASA is an important anchor tenant, one of the most important customers. But we've got a lot of other customers that we're developing towards that market. So there's a tie-in on the industrial engineering side. Because one of the things that we do in the model and analysis space is discrete time models. So in a lot of the industrial engineers, they work in software packages called Arena and things like this. And they develop these models to do optimization now. We've developed a model that models our operations in an industrial engineering type sense using a discrete time model that we integrate the missions and the customers and the manifesting. We integrate a space segment that looks at all the timelines within the space segment. We have the ground segment, the timelines associated with the ground segment, because there's a huge portion of this optimization and process optimization that we do to predict the future state of our station. So we have a good handle on it from the ground transportation, the transportation side, because DreamJX from the work that we're doing there with NASA for commercial resupply contracts. And then we estimate what our market demand is in terms of NASA side, and commercial side in terms of payloads and people, and how do we manifest those? How many vehicles do we need? How do we need to size our ground facilities so that we can do the refurbishment of our vehicles? How long is the vehicle in space versus how long it's in the ground? And what's interesting is when you look at it from that perspective, as spacecraft developers, we focus on space a lot. Turns out your big drivers are all on the ground in terms of timelines. That's interesting. Yeah, that is really your driver within the system, because once you're in space, you understand your customers, how long they want to be there, but the turns on the ground, the sizing of the systems on the ground become much more important. So that's when you talk about factories of 500,000 square feet to manufacture spacecraft, to do the refurbishment of the transportation vehicles. That really services, the space segment where you're talking about 1,000 cubic meters of volume. So your ground timelines are a big important piece of that. It's something that's sometimes subtle and missed, and that's something that certainly the industrial engineering world is doing too.
Our thanks to the team at Kennedy Space Center who originally shared their work with Problem Solved. When Keith and David visited Kennedy Space Center in 2022, Artemis 1 was still sitting on the launch pad, and many of the systems you heard about in this episode were being developed for a future that was only beginning to take shape. Thank you for joining us for this special From the Archives edition of Problem Solved. Be sure to follow wherever you listen, and we'll see you next time.